Hello, welcome back to the class. So today we will continue what we uh, did in last class, which is this example and question 1. So we have designed the data bus and also the CU, the control unit for this one, and also we have simulate the design. We write a Verilog code for the design, and we have simulate the design. And in the notes, this is one of the example of output, the input and the output for the design for the circuit. So we can see that when we give another input, yeah, A is 2, B is 4, C, D, E, right? And this is the result, and we can verify this by having this number in the equation, and we can get this result. Means that our design is correct. Yeah. And now before we try to do this, the question number 2, so let's get back to the code for the yesterday example. So one correction though, we have one correction here. This is actually, if we look at here, right, the multiplier here. So the last one is there's a mistake here, which is this one is actually R2, and for 1 1 multiplexer, this one is 1, this one is 1, should be R3, and another one it should be R2. So this is R2 and multiplied by R3 actually, right? So the question is why our simulation is correct if we have this wrong. The answer is that it's because that option actually is never used, yeah, because we only use this option for multiplier to multiply by R2 multiplied by R4 and R1 multiplied by R3 only. So if we look at here, we only used R2 multiplied by R4 and R1 multiplied by R3, these two options only. All right, these two options, yeah, 0 0 and 1 1, are never used, yeah, in to implement that equation. So why do we have this if we're not using it? So this is actually to implement yeah, because we design the hardware and we have the multiplexer here like this. So we need to have all the option, all the connection, right, that connected to this multiplexer. So this will include this and this, although we never use it. Okay, so change this to R2 multiplied by R3, right, to represent exactly what we have here. So now let's go back to this. We want to apply cost level restructuring on the equation of x. So this x. So here when we observe this, we can actually do something on x to reduce the hardware complexity, right? We see later, to allow for minimal hardware implementation. All right, derive the DFG and design your corresponding data path applying the constraint resource allocation of one multiplier and one adder. Okay, now before this we don't have any constraint where we can use, yeah, up to 3 adders in one cycles, means that we have 3 adder hardware here. We have 3 adder and 1 multiplier, right? This is multiplier. So, but in this question, we constrain our design to have only 1 adder and 1 multiplier. So we cannot use this design, and we need to have a new schedule and allocation, and of course the DFG, because we need to rearrange this equation, the x. Yeah, so when we look at this equation, we can see that we have a plus c in y, and here we also have a plus c. So actually we can group this one, all right, together, means that this is the same computational computation block. So we can use the same one actually, rather than have two computational block like this. Yeah, a plus b and plus c again. So right, instead of have the equation like this, so we can rearrange to be like this. Okay, so we have this equation x. So actually we can rewrite x to be like this. So we can see that now we have this a plus c, and in y we have a plus c. Okay, so we can share the same computation block for these two operations. All right, so this means that this is the same operation, right? So when we design our DFG, so we can have something like this. We have a plus c, so we can start with a plus c right here. We can have a plus c and right, a plus c and plus b multiplied by e, and we can have plus b. Okay, so we have plus b here, plus b, and multiplied by e, we can have x. Okay, so this is for f. And what about y? A. So we have a plus c already. So we have a plus c, yeah. And now we can have only this c plus d in here. So this is the same c. So we can use this one for c, and we have d plus, and we can have this, and then we multiply by this one, and we get y here. All right, so this is our new DFG, where we can see that this operation now shared together. Here we have this. Okay, now from DFG we will have our Now from DFG we have our scheduling and allocation. So let's do that. Okay, now we want to create the scheduling and allocation for our design. So maybe we can look back to our DFG here, and let's have a label here so that it's easier for us to create the schedule and allocation. So let's name this node as A1, means that A1 is this. All right, and we have this as C1, and we have this as B1. Right, so the first one is to get A1, right, in the first clock cycle. So here we can have this as S0, and this is S1, and we have S2. Okay, so we will have in R1 we load A into R1, and we can have C into R2, right, and we can have this operation, the plus, and we can save the result in R1. Yeah, and this should be our A1. All right, and the next one will be this, but remember that we have constrained our design to have only one adder, right, to use only one adder and one multiplier. So these two operations cannot be performed in the same clock cycle. So this one should be performed in the next cycle. So instead of having in the same clock cycle, so we can bring that into this cycle. So let's have that. Okay, our C is in R2, so we need to bring this to the next one cycle. So we can just bring this like this. All right, and D we can have here. This is D in this is not R1, this should be R2, and this should be in R3, right, because R1 and R2 is not available, so we need to have a new register which is R3. So this one we plus to get in this one we can save in R2. So this should be C1, right? We can see that we have one adder here and one adder here, right? And the next one is to have this operation and this operation, and these two operations can be done in the same clock cycle because this is a different hardware block. All right, this is adder and this is multiplier, so the constraint is still satisfied. So now we want to have B1 here. So B1 is B plus A1. So we need to have B available in the register because B is not in the register yet. So here we need to have, because we want to use A1, so A1 must be here also. So it should be still in R1, right? And we need to have B here. So because we use R1, R2 already, but here D, we don't use D anymore and should be available here for R3. So we can save in R3. right, for B, and we can have this plus, and we can use R3 for B1. So this is B1, and then we want to have this A1 multiplied by C1 to get Y. So of course our A1 is in R1 here, A1 multiplied by C1, we have Y here. So we can have a multiplier here. Multiplier, and we can have in R1. So this is actually Y. Right, we have Y here already, and another one is to have this X, which is E multiplied by B1. And now we have B1 already here, but we don't have E yet, so we need to have E here. And look what is the register that available? Only R2 available here, so we can use R2 here for E multiplication, multiply, and we can save the result here to get X, and this should be in R2, right? So this is our schedule and allocation. So we can see that here we use only one adder, right? In this cycle, one adder. In this cycle, also one adder. In this cycle, also one adder, one multiplier. So still satisfy the constraint. And this here we use one multiplier, and this of course will be S3, and we have F S4, all right, the cycle. Now we want to design the data path, so we need to have the RTL code for this one. So of course the RTL code can be easily derived from this schedule and allocation, right? So let's do that. So for the first cycle, so very easy, we can see that R1 is loaded with A, R2 is loaded with C, and for this one, the first one is R1 is this R1 plus R2, and we have this R3 D, and for this one we have this operation, this should be R2 plus R3, and this one is R3 loaded with B, right? And for S3 we have R1 is this R1 multiplied by R2, and R3 is R1. Hold on, this one is multiply, and R1, this one is R1, this one is R3, R1 multiply plus R3, and we have this. We have this R2 E, right? So we have 3, and here we should have another signal because we have Y already available. So we have Y done equal to 1, right? And the last one is easy. So we have R2 R2 multiplied by R3, and we have X done equal to 1. Okay, so this is our design, and we can see that by constrain our design to one multiplier, right? Okay, by constrain the design, right, to have only one, right, only one adder and one multiplier. We can see that here we need how many clock cycle to complete all the operation, including this one S0. Yeah, the load data 1, 2, 3, 4, 5. So we have 5 cycle for this one as compared to without any constraint. Yesterday, the previous video here, we don't have any constraint here. We can see that we can have as many as we want the number of hardware in the same clock cycle, in this case 3. All right, so we can see that here, yeah, we need 1, 2, 3, 4 cycle only as compared to this one. Means that with constraint, yeah, the speed, yeah, this one means that this one is slower in terms of execution because it needs 5 cycles to complete the operation. All right, whereas before this one is faster because only need 4 cycles. But although this one is slower, but we can see that we save cost a lot, yeah, from 3 adder to only 1 adder. All right, so we reduce the cost a lot, but the speed is just a little bit slower because only 1 clock cycle more than the previous one. So this design should be better in terms of cost. And of course, when you lower the cost, yeah, the size of your design, so this will also reduce the power consumption. All right, because if you have a large circuit, right, a big circuit, so that will increase the power consumption of your design also. All right, so by doing this, all right, have one adder and one multiplier, so we will reduce the cost and also reduce the power consumption. All right, although a little bit slower. All right, so this is good. And now let's see how to create the data path for this. Right, so again, to have a data path, so we need to refer to the RTL code here. So we can we need this RTL code. So to have our data path, we can look at the RTL code here. So here, how many register we need to have. So again, we have R1, R2, R3. So we can draw that. 3 register only. So we can have R1, R2, R3. All right. So again, we can see that the number of register also reduced, yeah, from 4 to 3. So and we have how many hardware? We have one adder and one multiplier only. So we can have okay. So let's this be our R1. This is R2. This is R3. So we have one adder and one multiplier only. So now again to create the connection between the register and the computation hardware here. So we need to look at our RTL code here. So let's see. So this is for R1. So we have how many input to R1? We have here A. We have from the adder, and we also have from the multiplier, right? So we have 3 to go to R1. So of course, if you have 3, you need the multiplexer, right? Before you can have your data into your R1 here. So first is from A and second is from this and this. So we have all of the output must be from this. All right, and we can have from this. Okay, and another one is from A. Okay, so we have this A, and we have from adder, and we also have from multiplier. What about R2? R2 we have from C, we have from adder, right? From C, from adder. We also have from E, we also have from multiplier. So we have 4 input to go into this R2. So of course we need the multiplexer, and multiplexer is 4 to 1. This is 4 to 1 also. All right, but we only use 3 of them. So we can have from the adder. So we can use here. And we can have from the multiplier. We can tap the signal from here. And we can have from B. Is it from B? R2? R2 is from C and also from E. So C and E, right? And what about R3? So R3 you have from D, you have from B, and you have from adder, right? You have 3. So you can have from adder. So this is from adder. And of course you need the multiplexer also. And this is how many? 1, 2, 3. So for the 1 multiplexer as well, right? So this is from the adder, and you will have from D and B. So you can have B, you can have D here. Okay, so that is from this, the connection, the input for R1, R2, R3. And now the input for the computation blocks from the for the adder and also from the multiplier. So again, we need to look at the RTL code. So first look at the adder. So for the adder, we have this, and this. So let's we rewrite here. So we have the first one is R1 plus R2. The second one is R2 plus R3, this one. And the last one is R1 plus R3. R1 plus R3. Well, we can have, there are many combinations here. We have R1, R2, R1, R2, R3, R3. So there is no other way. We need to have both of the input to the adder here. We need to have the multiplexer. All right. So we can have this multiplexer. We have 2 multiplexer. Okay, so here, let's, for example, we have this. Yeah, maybe we can use R1 and R2, and this one is R2 and R3. So we can have, this one is R1, another one is from the R2. Go to here, and for this one we can have R2 and R3. R2, and we can have R3. Yeah, so this will be the adder, input to the adder. And let's look at the input to the multiplier. So multiplier, we have 1 and 2 here. All right, 1 and 2 are this one and this one. So let's rewrite again. We have R1 multiplied by R2 and R2 multiplied by R3. So because this one is R2, this one is R2, we can actually change this to be R3 multiplied by R2, so that this one no need to share. Yeah, this, because this is always R2, so we can have something like this. This one is from R2, and the other one is you share this one, R1 and R3. So here you can have, one is from R3, another one is from R1. Where is R1? So this is R1. So you can have that for R1. All right, so that will be the data path, and of course we need to label all the signal. So this we should have LD1 for R1, LD2 for R2, LD3 for R3, and we need to have the control signal as well. Let's name this as SEL1. Yeah, and this is 0, 1, 2, 0, 1, 2, and name this as SEL2, as name this as SEL3, and this is 0. This we hold on. This we have 4, right? So we should have 1, 2, 3. Okay, and this one is 0, 1, 2 only. And let's name this as SELA1, right? 0, 1, SELA2, this is 0 and 1, and this is SELM, plexer for the multiplier, and this is 0, 1. Right, so all the signal, control signal. So for this, we can calculate our CV already, how many bit we need to have for CV. So let's look at this. So we have this one is 2 bit, yeah, because this is max 4 to 1, 2 bit, 2 bit, 4 already, and then this is 2 bit also, 6, right? This is 1 bit, 1 bit, 1 bit, 6, 7, 8, 9, and this load signal 10, 11, 12. Yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 bit for CV. So from that CV, we can have our CU block diagram already. So to have CU block diagram, so we can draw this. Right, so this is state register, and we have the next state logic. We have the output logic for the CU. Next state logic, and this is state register, and this is output logic, and we will have the connection from here to here. And what is the size of this one? So again, we need to look at our this, yeah, how many cycle we need to have. So we need to have 5 cycle, 1, 2, 3, 4, 5. So if 5 cycles, we need to have how many flip-flops? So we need to have 3 flip-flops, yeah, because 2 flip-flop is not enough. 2 can represent until this, yeah, 4 cycle. So if we have more than 4, right, in this case 5, so we need to have 3. So here should be 3 bit, and here also 3 bit. Yeah, and of course we need to have the feedback to this, the FSM need to have this, and this one is negative age triggered, and you need to have reset, and the CV is this 12 bit, and we have this signal. Remember, this 2 signal is the output from the control unit as well. So you have this X done and Y done. All right, so this will be your CU. And this is your DU. Okay, so from that CU and DU, you can write your Verilog program already. But before that, we need uh, to derive the control vector based on, again, the data path and also the RTL code. Okay, so we can have this. Okay, so this is example of the CV for this. Yeah. So let's see. All right, so let's look at this. So for example, for the first cycle as 0, so we want to load A to R1 and load C to R2. So what to do? So A, the SEL1, which is 2-bit, SEL1 is 2-bit, must be number 2, or in this case is 10. Yeah, and LD1 must be 1 to load data into R1. And for SEL2, we want to load C to R2. So for C, the number is 1. SEL2 must be 1, should be 0, 1 in binary. C is 2 also, must be 1, 0. Yeah, and LD2 must be 1. LD2 must be 1 to do that, right? So for this one, we want to do add R1 and go to R1. So means that the data to the R1 is from the adder. Okay, and from the adder, SEL1 must be 0, so that we have 0, 0. Okay, and to add R1 and R2, so make sure that this one is R1, so should be SELA1 should be 0. Should be 0 here, right? And plus R2, so where is R2? Should be 0 also. SELA2 must be 0, so that we have R1 plus R2, right? And we want to load D into R3, so R3 need to load D, so D SEL3 must be number 2 or 10. SEL3 should be 10, right? And load LD3 must be 1. And this is the hexadecimal representation of this, right? And this one is hexadecimal representation of this one. And we have this, yeah, 0, 5, 8, 5. So this is 0, this is 8, this is 5. All right. And for the others operation, we need to check one by one also. And this is the things that we need to have. All right. The CV that we need to have for all the cycles here. Okay. So from that, we can write the Verilog code already. Okay. So let's look at the Verilog code. So for that, I have the code already. So let's go to that. So this is the code for the DU. So let's look at this. So this is our DU, and this is the code for this DU. So we have, of course, we have the clock, we have the reset, we have the CV, which is which are all the signal here, control signal, and we have the input A, B, C, D, E, A, B, C, D, E, and we have these R1, R2, R3. We will have something like this. Yeah, we connect this to the output so that we can see in our simulation that the content of R1, R2, R3, what happened to this inside R1, R2, R3. Okay, so we need to list in the port list as well, and input is of course clock and reset, and all the input here are 8-bit, and our CV is 12-bit. Yeah, 11 to 0, 12-bit, and output, yes, this one is set to be output, and need to declare as right as well, because we describe the register here using behavioral modeling inside the always block later on, so need to have right data type for this one, and this is the signal for this. Yeah, this we name as and this one is right add out, and mod out, and the size is of course 8-bit. So this one is 8-bit, this one is 8-bit. All right, and all the input are 8-bit. Okay, so, and we have set all the control signals to be wire. All right, SEL1 here is 2-bit, right, because this is 4-to-1 multiplexer, so need 2-bit as a control signal. SEL2 also 2-bit, SEL3 also 2-bit, so all here are 2-bit. And for SEL1, SELA1, A2, SELM, LD1, LD2, LD3 here, A1, A2, SELM, LD1, LD2, LD3, all are 1-bit. So here, and now we connect this to the CV signal that we create. All right, so SEL1 bit number 1 is connected to CV bit number 11. SEL1 bit 0 is connected to CV bit number 10 until we have all here. All right, so this is just to connect this for the CV, because we group the output of the input here for the control signal, which is the output of our CV here. All right, is 12-bit, right? So in here also you need to have 12-bit for that. All right, so and this one is for good for the R1. Okay, this one is R1, so we can see that here R1, so we use post age clock. Post age reset means that the reset is asynchronous active high reset. Yeah, means that if 1 means that this register will reset, right? So if reset equal to 1, so R1, R1, the output here is equal to 0. And if not reset, so we will look at the load signal LD1. So if LD1 equal to 1, means that we will look at the input here. So the input here will depend on this one. All right, the multiplexer here. So because we have 4-to-1 multiplexer, we can use case statement. So if 0, 0, so the output, the content of R1, or the output here R1, should be equal to this. Yeah, if 0, 0, so add out. So this is add out. And if 0, 1, 0, 1 should be from the multiplier. That's why we have this, right? And if this 1 0, so we have from A, and actually 1 1 we don't use, so this one you can have don't care or 0. In this case you can use don't care. All right, if 1 1 you don't care. For R2, which is a 4 to 1 multiplexer as well, so it should be no problem. Should be the same as the previous one, except that the output here is R2. All right, and LD2, if LD2 equal to 1, so we do this. All right, select if 0 0, so the here the input to R2 should be add out if 0 0, so from the add out, if 0 1 from the multiplier. All right, mul out. And if 1 0, we have this from C, and if 1 1 we have from E, right? And this one we have all these possibilities, so it's okay. And for R, this should be R3. For R3, so R3 here should be the same. We have R3 if reset 0, and if load 3, LD3 equal to 1, so we will look at this multiplexer. So case SEL3, if 0 0 add out, if 0 0 add out, if 0 1 from B, if 1 0 from D, and if 1 1 is don't care. All right, we don't use that. And this is for adder. All right, for adder. And again, when we look at this, we have 4 here. We have 2 multiplexer. All right, 2 to 1 multiplexers, but we can combine that actually, right, to have something like this. Because if 0 0, we can see that if 0 0, the output, yeah, at out here is equal to what? R1. If 0 0, yeah, R1 is equal, R1 is add to R2, so that we have this. And if 0 1, if this is 0 and this is 1, all right, so it should be R1 add to R3. That's why we have this. And if 1 0, if this is 1 and this is 0, so the output here should be R2 plus R2. So we have R2 plus R2, right? And the last one will be 1 1 if this is 1. So we have R2 plus R3, right? And here we have all of the combinations. And we can see that here we will not use, just like the previous example, we will not use all of this option, yeah, because in our RTL code we only use this R1 plus R2, R2 plus R3, right? R1 plus R2, R2 plus R3, and what else? R1 plus R3. We have R1 plus R3 here, and that's it. All right, we have 3, 1, 2, 3. So we don't have R2 plus R2, but to design the hardware, we need to have this, yeah, all the possibilities for this circuit. Okay, so the last one is multiplier. Multiplier is easy because we have only one multiplexer here, so this one is always R2, so we can have something like this. Yeah, if SEL M equal to 0, so the output here, if this is equal to 0, the output here should be R2 multiplied by R1. All right, R2 multiplied by R1. If SELM equal to 1, right, so it should be R2 multiplied by R3, like this one. Okay, so we have that for the DU. What about CU? So this is CU, and to have CU we need to look at this. Okay, so this is the CU, And we have clock reset CV, all right, clock reset CV, and we have X done, Y done, and we have another output. The name is state. So this one is for this one to for the simulation. We want to observe or want to see, right, the state transition in our simulation. So we can have this. Okay, input, clock, and reset. All right, we don't have any external input, so only a clock and reset for our input. Output, we have CV, so CV, and then need to declare as rect as well, because we will use the always block to describe the CV. State is 3-bit, 3-bit. This is 3-bit. This is state. Output, X done, Y done, 1-bit, and rect also. Okay, and we have this signal. We name it as next state, right, for this signal, next state. And the name of our state, all right, S0, S1, S2, S3, S4. We have up to S4, right? State register is easy. So to define this is how we have negative H triggered clock, negative H triggered, and we have reset, positive H, or asynchronous reset, positive active high. If reset, of course, the state, the output of this, it should be equal to 0, and S0 is this 0. All right, else the state here is this next state. All right, so this statement, next state. And now we want to define this and this one, and again this the CV is depend on this state signal, and also the next state logic also depend on this state signal. So we can write like this, always state, and case state, all right, because we will have many possibilities, all right, state, and state is 3-bit, so you can have up to 8 possibilities, right? So you can use case statement. So for example, if state equal to 0 or S0, all right, what is the output here? So the output here should be CV equal to what we have here, which is 0 A06H, right? A06H, and the next state will be S1, all right? If we are in S0, the next state must be S1. The next one should go to S1 because based on our design here, right? S0, we need to go to S1 in the next clock cycle. Okay, so just straightforward there, S1, and in state S0, so X done and Y done should be state 0, so we have 0, 0, and here this is the first statement, right? And next we have S1, so CV again, S1 CV should be equal to 085, 085. Next state should be S2. When we are in S1, we go to S2, and still X done and Y done equal to 0. Yeah, right. And next is S2, and this is the CV. Again, based on this, 073, 073. The next one is 717, 717, and the last one is 10A, 10A, and this should be the state S1, S2, S3, S4, and go back to S0. And we should remember that at S3, Y done should be equal to 1. So we can see that Y done equal to 1 here, and S4, X done equal to 1 here. And because state is 3-bit, so we need to have all the possibilities definition. So we need to have default, means that other than this, the output CV should be all 0, all right, or don't care, also can. And we still always stay at 0, and y done equal to 0, x done equal to 0. And this should be the CU, and the connection between CV and DU is this, right? So this will be based on this, because we have now is this CU and DU, all right? So of course from CU to DU, you send this CV, right? And this CV is how many bit just now? 12 bit, 12, and this is positive H clock, this negative H for this one, and we have positive for this one. And you have reset, okay. And from CV also you have one output called state. This is for to look at the state transition in our simulation later on. And this is 3-bit, and we have 8-bit input for A, we have 8-bit for B, C, D, and E for the input to the DU. So this is DU, this is CU, and for the CU you have output, which is R1, this is R2, 8-bit also, and you have R3. Right, so this is for simulation purpose only. We want to see what is inside R1, R2, R3, so we need to have this set as output also. And of course we have this y done, we have this x done from the CU, right? So now we want to create this, so we can have this, so the port list is all the port here. So we have clock, we have RST, we have A, B, C, D, E, A, B, C, D, E, R1, R2, R3, R1, R2, R3, and we have X done, Y done, and also state, X done, Y done, and state. All right, so clock reset is input, A, B, C, D, E, 7-bit input to this. Output, we have R1, R2, R3, and also the state, 8-bit here, and 3-bit here, and also output is X done, Y done, and we have wire CV, this one, 5-bit, this one, and now we instantiate the DU, which is this one. So how to instantiate? So just have the same input port arrangement like this to this, and name as DU. All right, this is the module name, which is this one, this, right, and the CU also the same, and done. So this will create this for you. All right, so for the simulation we have this is the test band for this, and we give the same same input as the previous design. A equal to 1, B equal to 2, C equal to 3, D equal to 4, and E equal to 5. And let's see Yeah, when we simulate what we get. So this is the output. Yeah. Okay. So the waveform. Okay, so let's set this to be a sine number so we can see the output clearly. So this should be at S0. So we load all the value, not all the value. So this is the value is set to be 1, 2, 3, 4, 5. All right. S1 we load 4 into we load D. S1 we load this A. Yeah, 1 into R1 already, and let's look at the output. So at S3, state number 3, all right, so according to our schedule, so as at 3 we have Y done equal to 1 already, and Y should available here. So R1 is, yeah, this is R1 20, R1 is 28. So this is Y done equal to 1 done, yeah, in this case. So we have the result in R1, which is here. R1, see, this is R1. R1 is 28. So just like we just like we have yesterday, just like we have in the previous video. Y y should be equal to 28. All right, based on our equation. Yeah. Okay, so if A equal to 1, B equal to 2, C equal to 3, D equal to 4, and E equal to 5. So we should have Y equal to A1 plus C equal to 3 multiplied by 3 plus D equal to 4, which is 4 multiplied by 7, which is 28. Yeah. For X, we have E is 5 multiplied by A equal to 1 plus B equal to 2 plus C equal to 3. So this is 5 multiplied by 6. We have 30. All right. So we can see that X is 30. So here X should be inside R2 based on based on this, X should be in R2 and the value of X should be 30. All right. So X is available in the clock number 4 or cycle number 4. X done is here, X done, and this is 30, right? So we have the output like this. So this proof that this is the same give us the same output as the previous one. The only difference is that this need 4 clock cycle as compared to the previous one that we need only 3 clock cycle. All right, but again, this one is better in terms of the cost and also power consumption, with slightly slower as compared to the previous one. Okay, so that will be the answer for this. All right, and again, this is applying ALAP as late as possible register allocation. So when we look at our design here, this is actually ALAP. Okay, where when we look at this is as lead as possible register allocation, ALAP. Why ALAP? We can see that here R3 we not loading R3 in the first cycle. If we do that, this will be ASAP, right? Because we want to use D here in S2, so we load in S1 just before the operation. So this should be as late as possible. Same as here also, all right? So when we want to use B in S3, all right, we load B in S2, all right? So this will be as late as possible. We're not loading B before that. If you load before that, S1 or S0, so that will be as soon as possible, right? And also here we have this E, late, just before the operation here. So this is the LAP register allocation. All right, so that will be the answer for this and also for this in the previous video. So after this, we will look at this design optimization and performance measure in the next video. Okay, thank you.